Hey, Physics 30. So today in this lesson, we're going to be talking about the relationship, obviously is what it says on the screen there, relationship between magnetism and electricity, and how those things kind of connect together. That's why this is the second part of Unit 2. So if you haven't done already, pause this video, go and watch the Crash Course Physics magnetism video. Be very leery about the hand rules they use. They're using what we call the right-hand rules because the video is produced in America. They like America. They like to use the right-hand rule rather than use the left-hand rule because they are stuck in old convention where they believe the flow, or they don't believe it. Obviously, they know that flow isn't positive charge, but the hand rules they use talk about how current is the flow of positive charge, but what we know, current is not the flow of positive charge, is the flow of negative charge. So we're going to switch our hand rules a little bit, and we're actually going to talk about a left-hand rule for negative charge and a right-hand rule for positive charge. But there's a lot of good information in that video talking about angles of how the angle of the charged particle and the angle of the wire determines how much force there is. Who discovered this relationship? So one of the main things that they talked about in that video was the physicist Oersted here. He accidentally discovered this by bringing a compass near current carrying wire. After Oersted discovered this, everything started snowballing. They started creating electric generators. They started producing electricity from motion. It's just a very quick motion to that. So, or a quick progression through technology to get to where we are now. So, what we know so far is this is a pretty layman way of what his experiment was. He used these nice little wooden clamps. Wood is a pretty good insulator. He used this nice little bare wire. They didn't have insulators on wires. He had a Volta pile up here. A Volta pile, very much like Alexander Volta from chemistry. It's just a bunch of zinc and copper. It's a pretty high power battery. Lots of current coming out of this. You need a lot of current to actually see this experiment work. You have this wire kind of running through here, and you have this compass sitting underneath the wire. So right now you can see that the compass is pointing north. So you can assume that that's the geographical north, that direction. Remember the last video we talked about how that's the actual magnetic south pole is up in that direction, right? Because the magnetic south is where the geographical north is. So we have this nice little compass pointing in that direction. So he turned this on. And when he turned it on, he just connected the battery up here. Current is flowing through here. Actually, the current is flowing the other direction. We're not too concerned about that. What he was concerned about is, so that the compass now has changed its direction. It's actually not pointed north anymore. It's pointed perpendicular to the wire itself. Okay? And he flipped the battery. You notice that the compass flipped the other direction, still perpendicular. And he turned it off and went back to the north. Turned it on. Turned it on and went back perpendicular. So if I move this around, it'd always be pointing perpendicular to the wire. Okay? If I put it above the wire, it'd be pointing the other direction. If I put it below the wire, it'd go the other direction as well, back to the same direction. Now this is the same kind of experiment. Instead of a compass, he just used a bunch of iron filings. He put a bunch of iron filings on top of a piece of paper. He ran a wire through it, and then he turned on the wire. And then he noticed that all the iron filings kind of went around in this nice little circular motion. If I were to put a compass here, it'd be pointing sideways, perpendicular to the wire. If I put a compass over here, it'd be pointing this way, perpendicular to the wire. It'll always be pointing around the wire in this direction. According to this little picture, it's going around that direction. So this is a very similar diagram, but this one's actually more animated. So these little, you can see how this kind of works out. So you can see the arrow here is the direction that they label conventional current to go. But the little particles, those are the electrons. Electrons are flowing upwards and the arrow is going the other direction. So the electrons are flowing upwards. And if you remember from Veritasin's video, the movement of charge, the movement of these electrons is going to produce a magnetic field. So these electrons are moving. If they weren't moving, they wouldn't produce a magnetic field. They would just be a static field there, electric field. So they're moving upwards. They're going to produce a magnetic field. And we have this little compass on the side. So if I move this compass around, you notice that this compass is always pointing perpendicular to the direction the current is flowing. Okay? And it's always pointing in this little concentric loop here. And you can see up in this little picture here, you've got these nice little loops going around. I can move it closer, I can move it further away. But the compass is always pointing in one direction around the wire in a certain direction. In this case, if you look down on top of the wire, it looks like it's kind of a clockwise direction. If I reverse it, now the currents or the electrons are moving downwards. It's going in a counterclockwise direction here. Okay. Now, these are great pictures. They're nice three-dimensional pictures. You can see the cross section. You can see these nice little loops. How would I draw this on paper? How would I see this on paper? But let's just highlight some things on this page before I go here. So what he discovered, and the very key part, is that current carrying wire produces a magnetic field. Current carrying wire. So the main part of his discovery is that moving charge produces a magnetic field. All right, so moving charge, positive or negative. All right, they believed back then it was positive charge moving. We know now it's negative charge moving, but you can also throw positive charges through space, like a proton or a positively charged ion, and they can produce magnetic fields as well. So how do we draw this kind of stuff on paper? Well, we have to, because everything's kind of going to go in like three directions here: up, down, left, right, in and out of the page. So we have to kind of denote this extra dimension. So rather than just having up and over, now we can have into the page and out of the page. We usually don't draw the circles around them, but an X here denotes something that's going into the page. A dot denotes something that's coming out of the page. Those are our three dimensions now. We have up, down, left, right, in the page, and out of the page. So the X here, you think about if you're shooting a bow and arrow, as the arrow leaves you, you would see the feathers, the end feather, as the arrow kind of goes away. And if the arrow is coming towards you, you would see the arrowhead, the dot of the arrowhead, come towards your face. So that's what you're kind of looking at here. So you're seeing an arrowhead coming towards you out of the page, or you're looking at the arrow go away from you. So you're seeing there's just the feathers going into the page. Now, what you're going to see if you go into university and do current and electricity and magnetism, you're going to see this used a lot, conventional current. It really depends on how old your professors are, or how old the textbooks are, or where you do your university. If you do it in the States, you're going to use conventional current a lot. Now, in Canada and most of the world, we like to talk about electron flow because that's what we are, but that's what's actually happening. Electrons are flowing through the wire. But if you go to the States, or you have an older professor, or you look at some old textbooks, or you look at some videos that are produced online, they're probably going to be talking about current as conventional current, which is the flow of positive charges. Now, we know that flow, current is not the flow of positive charges, but this was the early thought of what electricity was, so it became convention. That's why it's called conventional current. It just kind of stuck. And what we know now is electron flow is actually what's happening. It's the flow of electrons in a wire, and this is actually what's happening within the wire. Now, if you were to draw a wire, let me just draw a wire out here. Here's my wire, and I would have conventional current flowing one way. Electron flow would be just going the other direction. Conventional current is usually positive. Okay? Current, either one doesn't really matter, is denoted by the letter I. Okay? I think I'll talk about it later on in a different video. But current is denoted by the letter I. It's usually measured in amperes, right? Or amps. And it represents the charge per second, how much charge passes a certain point every second. So that would just be the flow, how many electrons would pass by every second as well. But it'd be coulombs per second, usually measured in amps. We're going to talk about this later on, but that's what an ampere is. It's a coulomb per second. Okay, so we have these new ways of representing direction. In the page, okay, in the page, out of the page, left, right, up, down. Okay? So this picture here is just kind of the same picture from this diagram that we have here. So we have this compass that kind of flows around this wire. Let's just move this sideways. That flows around this wire. It's always kind of pointing perpendicular to the wire and the direction of the field or the flow of the electrons. Never pointing, it doesn't point in towards the flow of the electrons. That would be technically perpendicular, but it's always going the other direction. All right? So it's running kind of parallel, I guess. I don't know how you would describe that, but we can draw this out. So this is our little piece of paper again. We have flow going through the wire. So this is my wire here. So let's just label the wire. And what we're going to do is we're going to just put some current going through this. And we're going to do it with electron flow. So my electrons are flowing down through the page. So my electrons are flowing down through the page. Okay. And what we know is I can draw this out. So I can draw out these little compasses. And these little compasses are going to kind of point in this direction, as if there's a circle around this. And what a compass does, it just aligns itself up with a magnetic field. So there's going to be a magnetic field produced here based on what the picture says, or that animation says. So there's a magnetic field. Actually, I don't know if that's the proper direction yet, but I know it's going to go in a circle around here. So my magnets, my little magnets inside the compasses are going to line themselves up with those compasses, or with that magnetic field there. So this little red line here, that's my magnetic field. Now, they would line themselves in that direction. Now, there's a rule. It's a hand rule, and I think that's on the next page here. Yeah. Next, there's a hand rule that tells us the direction of this current flow. So what I know, based on the hand rule that I can quickly do here, is that these little magnets, these little compasses are going to point in this direction. Yeah. They're going to point in that direction, where all the north sides of these magnets are pointing counterclockwise around here. So if I were to draw more magnets around here, so I could draw some more magnets right here. Now let's just make these a little simpler, not little arrows, but these little compass arrows are going to point in a counterclockwise direction around this. So this would be the north side here. North, 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 north. They're all pointing in the same direction there, in the same circular motion. So there's a big field going around here. So a big circular field going around. Now, how we know that is that we pulled our hand out. Now, what I'm going to do is I'm just going to pause the video and just change the direction